Hello, my name is Bohyun Wang, works as a research professor in AI Lab of Gachon University. I will give you a presentation for feature selection method. Paper title is Embedded Feature Selection by Distance Measures of Subnormal and Non-convex fuzzy sets. Contents are as follows. First, I will tell abstract and introduction, and then I will explain the proposed contents. And last, I will show result and discussion. Abstract. In this paper, several concepts appear. Distance measure of fuzzy sets is concept for feature selection and finding redundant features. Distance between fuzzy sets can be measured. This distance is used for feature selection and finding redundant features. Normal and convex fuzzy set as common definition of fuzzy sets is about the shape of a fuzzy function. This paper extends the normal and convex concepts to subnormal and non-convex for distance measure. Proposed idea is distance measure method for subnormal and non-convex fuzzy function for feature selection. Introduction. Neural fuzzy system is method to optimize fuzzy membership functions for the automatic tuning of fuzzy models. The shape of a fuzzy function in fuzzy system often lead to adjust to improve performance of system. At this time, neural network algorithm is used for adjusting the shape of a fuzzy function. We call this system as a neural fuzzy system. When we use a machine learning system, running target is features. The number of features can be as few as a few or as many as 1,000. Performance of machine learning depends on the number of features. So the number of features is very important, and the feature selection step is required. Computational complexity can be reduced using feature selection method. Discriminating ability of fuzzy logic systems can be increased by decreasing the feature vector dimensionality. The embedded feature selection are less computationally intensive and have greater interaction with the classifier. About distance measures, we already mentioned before pages. Distance measures is a method to select features in the machine learning preprocessing step. The way of distance measures of subnormal and non-convex fuzzy sets are proposed in this paper. In my lab, we possess self-developed neural fuzzy learning algorithm. The name is NewFM, which is referenced in paper. When learning is processed in NewFM, a fuzzy set for a feature is produced. During learning, height and width of a fuzzy set are adjusted. We call adjusted fuzzy set weighted fuzzy membership function, WFM. Weight is assigned to fuzzy function according as the importance of feature. After finishing, the shapes of whole fuzzy sets are different because of a different weight. In future page, we can see WFM. Final fuzzy set is like a subnormal fuzzy function. Bounded sum WFM, BSWFM, combines the subnormal linguistic variables into one by bounded sum operation in fuzzy set theory, forming convex or non-convex fuzzy sets. As the BSWFM merges all WFMs into one for each attribute, when more attributes are added to a system. The high complexity of the fuzzy rules can be reduced to a linear number for efficient inference, resulting in greater accuracy. This paper introduces a new embedded feature selection method called distance difference ratio, DDR, that efficiently measures distances between subnormal and non-convex membership functions, learned from a neural fuzzy classifier, NuFM. Parkinson's disease classification tasks using the proposed feature selection in this paper are demonstrated. I will explain the proposed method. Before the proposed method, elements that makes up the proposed method are explained. First, I will explain about subnormal. This figure shows subnormal fuzzy set and normal fuzzy set. This graph is fuzzy function. Normal fuzzy set means fuzzy function with x with a result of degree 1. In subnormal fuzzy set, the result of function are smaller than degree 1. In this figure, the green line is a normal fuzzy function. Black line is a subnormal fuzzy function. All the result is smaller than degree 1 in subnormal fuzzy set. Second, convex and non-convex. Convex and non-convex definitions is somewhat complicated, so I will show simple graph about this. Left-hand side is convex fuzzy set, right-hand side is non-convex fuzzy set. Convex fuzzy set is similar to symmetry, but non-convex isn't. Fuzzy sets produced in NuFM are subnormal and non-convex. This figure shows fuzzy set in NuFM. These fuzzy sets are produced in NuFM during running. For a feature, fuzzy sets of the same number as the number of classes are produced. 3 fuzzy functions are one set. During running of NuFM, these red points are adjusted according as the importance of a feature. Red points are adjusted in up and down and left and right. These red points means weights of fuzzy function. The 3 adjusted fuzzy functions are called weighted fuzzy membership functions. In this figure, 3 blue triangles are weighted fuzzy function. We call WFMs. One WFM is obtained by applying bounded sum to 3 fuzzy functions. And this is called bounded sum WFM or BSWFM. In this figure, black thick line, black thick line is BSWFM. From this page, I will explain core idea which is proposed. Before the page, I told that fuzzy sets of the same number as the number of classes are produced for a feature. That means BSWFMs also are produced as many as the number of classes for a feature. This figure shows overlapped BSWFMs of 2 classes for a feature. Overlapped BSWFM for a feature are gained after one learning. Even though there are many formulas, I will explain several concepts using this figure. There are three concepts: bounded difference, bounded distance, bounded intersection. Red line PSWFM area A, red dot line PSWFM area B. At this time, the white area is the intersection area of two PSWFMs. The black area, like this, black area is the area A minus B. The gray area, like this, the gray area is the area B minus A. We call white area by bounded intersection. We call black area or gray area bounded difference. We call black area plus gray area bounded distance. The core idea in this paper depends on bounded difference area, bounded distance area, and bounded intersection area. When any x value is input in this overlapped PSWFM, two values are output. This value is for class B. This value is for class A. Because the value for class B is larger than the value of for class A, x value is classified as class B. In order for this PSWFM to be good at classification, the difference between the two y values must be clear when x values are input. To do this, the smaller intersection area is the beta, and larger the distance area is the beta. The fact that the two distance area, black and gray, the fact that the two distance areas are similar means that the values constituting the feature are not biased to any one class. And it means that classes can be distinguished well. Through this meaning, this formula is gained. The larger distance, this symbol is distance. This symbol is intersection. The larger distance is the beta. Smaller intersection area is the beta. The meaning that difference of two difference area is low. Two difference area are similar. We calculate DDRs for whole feature and then sort DDRs. After sorting, we select good feature and bad feature. Good and bad features evidence can be presented through overlapped PSWFM. This pseudocode is very complicated, but we don't need to whole part. I would like to show this part. Whenever running is performed, the DDR values of all features are calculated, and the best point of the feature with the largest DDR value is increased by 1. Conversely, the worst point of the feature with the smallest DDR value is increased by 1. After finishing running, best feature and worst feature are decided by best points and worst points. Except best and worst features, other features have own points. We sort the best and worst points, and then we select several features for good features or bad features. This method is the method to select a feature. We can propose the evidence of good and bad features using this BSWFM. Finally, we came to result. This is the dataset we used in experiment. We got the dataset in the UCI repository of machine learning databases. The dataset was composed of 195 sustained vowel phonations from 31 subjects. 23 of 31 subjects were Parkinson's disease patients. We classified Parkinson's disease and normal condition. Some patients with Parkinson's disease had been diagnosed for less than 1 year, while others had been diagnosed as long as 28 years. The patient's age is between 45 and 85 years of age. Each patient recorded an average of 6 times. We normalized whole features. In the first step, we got a max value and mean value of a feature, and then we divide each feature value minus mean value by max value minus mean value. In the second step, using y obtained in first step, we divide y minus average of y's by standard deviation of y. The result is that in third step, we rescaled in the range 0, 1. 22 features are obtained. As a result, 22 DDRs are obtained. In this page, you can see two kinds of overlapped BSWFM with the best DDR and the worst DDR. Left overlapped BSWFM has a smaller intersection than right overlapped BSWFM. For the difference area, like this, difference area, left BSWFM is larger than right BSWFM. We removed the right feature, and then using remaining features, we run again. Table 1 shows the result of feature selection. For test accuracy, 19 features produced best performance. Table 2 shows comparison among other algorithms. UFM using proposed method produced the best performance. Discussion. In this paper, we propose DDR for feature selection. That is a distance measure method of subnormal and non-convex BSWFMs. Subnormal and non-convex BSWFM are weighted fuzzy membership function. After each iteration, DDRs were calculated and the features were then ranked according to those DDR values. Some features were removed by their rank, and the next iteration was then performed on the remaining features. The iterations were repeated until the accuracy did not improve. The proposed feature selection method was compared with two other methods, one based on probability density and the other on genetic programming. The results of the experiment demonstrated that 97.95% training accuracy was maintained even if the features were reduced. The accuracy of the test set was 93.9898%, which was highest when using 19 features. Moreover, compared with the other method, the method using DDR demonstrated higher accuracies for training and test of 97.95% and 93.98%, respectively. We observed that the accuracy was maintained even though the features were reduced in our experiment, indicating that valid features were selected using feature selection via DDR. The subnormal and non-convex fuzzy set can include more information and are more nature than the convex fuzzy set because it can be adjusted more finely and linearly by running enough to reflect the precise distribution of the actual data. Specifically, this means that there is a reduction in error through nature adjustment. The concept of difference area and distance area that are generated from BSWFMs of classes is based on the distribution of data included in each class. Therefore, it is very reasonable and logical that this concept can be used for selecting the features and classifying data. This study may impact the study of automatic feature extraction techniques that reflecting the characteristics of the data itself within various types of data sets. The experiment proved the effect on the accuracy of the non-convex fuzzy set containing rich aggregated information. In addition this, in deep learning area, black box of the learning process is one of the problem. User can know only the result, but cannot understand the reason why the result is output. In that respect, our proposed idea can provide explainable learning base. Thank you for listening my presentation.